Hi, in this video I'm going to continue on the topic chemical equilibrium, and in this video I'm going to start talking about factors affecting the chemical equilibrium. Now here I'm going to first introduce the Chatelier Principle, and after that I'm going to discuss how the change in concentration of an equilibrium system will affect the equilibrium position. So let's get started. Now when we have an equilibrium system, we say that the reactant concentration and the product concentration will not change, and the overall physical property will not change, right? Now, what if we have imposed a change onto the system? For example, we increase the temperature of the system. For example, we add some extra reactant to the system, or perhaps we remove some of the product. Now, these are possible changes that is happening on a system. And when a system is exposed to these changes, first of all, they are no longer at equilibrium state, right? So they are changing from equilibrium state to a non-equilibrium state, right? And secondly, the equilibrium system will actually respond to such a change, right? So down here in our discussion, we will talk about how the system responds to changes so that it can go back to equilibrium state from a non-equilibrium state, right? And also we will break it down different factors, right? For example, concentration, for example, temperature, for example, pressure, something like that. And how do these factors affect the equilibrium precisely, right? Now, here, let's highlight some key points. We say that when a condition of an equilibrium system is changed, okay, such as changing concentration or changing temperature, right? Changing concentration, changing temperature, right? Then the system is no longer at equilibrium, and we call that non-equilibrium state. However, the system will adjust itself. It will respond by adjusting itself in order to attain a new equilibrium, okay? To attain a new equilibrium, okay? Now, as to how we determine or how we can tell the system's response, we can use two different methods. Now, there are two ways to determine how a system will respond to such changes. The first one is the Chatelier Principle, the second one is reaction quotient. All right? Now, at this moment, I would say the first one is more of a qualitative approach. Qualitative approach. While the second one is more of a quantitative approach, okay? So perhaps the second one involving some calculation, the first one do not, okay? Now, so let's get started. The Chatelier Principle coming from the guy, a French scientist, so this one we call it the Chatelier Principle. Now, the Chatelier Principle, this one you need to memorize. You need to state very clearly what is meant by the Chatelier Principle. So let's underline the key words. The Chatelier Principle states that when an equilibrium system is disturbed by any change, right? When there is a change, then the system will change in a way to counteract such changes. Counteract such changes. The key word is counteract. Okay? Now, what do you mean by counteract? Now, for example, for a particular system, equilibrium system at equilibrium state, if we add some reactant into the system, now the changes will definitely be an increase in concentration of reactant, isn't it? Now, the system will counteract such change. That means it will counteract the increase in reactant concentration. So basically, to decrease the reactant concentration, isn't it? To counteract an increase is to decrease it, right? So this is an example of counteract. For another example would be if we increase the temperature of the system, then the system will counteract by decreasing the temperature. Okay, so now you understand what we mean by counteract. Now, let's look at this example and let's see how the Chatelier Principle can be used to qualitatively predict how a system will respond to such changes. Okay? Now, here we have a reaction reacts to form P. R reacts to form P. Now, here, look at this diagram. Like I said, this topic, very often the concepts are illustrated using diagrams. Now, so first of all, you can mask away these parts. Okay, let's start with the initial part. Now, initially, you see, we have some reactant, we have some product, but the concentration doesn't change. What does it tell you? Well, it tells you that they are at equilibrium states, right? Now, at a certain point, at here, what we did is we add some allo into the system. Okay, maybe we open the lid and then we add some R and then we close the lid of the beaker. Okay, something like that. Now you realize that the instant change to the system will be the increase in concentration of R. So you can see the concentration of R, okay, quickly increases. Okay, now as the concentration of R increases, such an increase in concentration would be the change to the system, right? For the Chatelier Principle, bear in mind, we need to recognize, we need to identify the change. Okay? If there is no change, we can't use the Chatelier Principle. So the first step is you identify the change, and the change in this case is the increase in reactant concentration. Now, so according to the Chatelier Principle, it says that the system will change in a way to counteract. So to counteract the increase in R concentration is obviously to decrease the reactant concentration. Okay? To do that, we will actually perform more forward reaction. We will perform more forward reaction because the forward reaction is exactly the reaction that can consume more reactant. Okay? Consume more reactant. So the system will change in a way to perform more forward reaction, or the forward reaction occurs faster. Okay? So you see, after the R is added, you see the concentration of R slowly decreases. Okay? That indicates that there is a net forward reaction consuming the R. Okay? Now, as R is being consumed, you can tell P concentration will increase because R becomes P, right? So when this one decreases, this one increases. Now, at this point, where you see, the concentration of R and P remain unchanged again. So what does it tell you? It tells you that at this particular point, we say that new equilibrium is attained. Okay? New equilibrium is attained. Okay? Because you see now the concentration, again, R and P not going to change. Okay, so that means equilibrium state has reached. Okay, right. Let's look at these description. Okay, so when the reactant concentration increases, okay, this is the change. Remember, this is the change. According to the Chatelier Principle, the system will counteract by consuming more reactants, right? It will counteract by consuming more reactant, so that the forward reaction will occur at a greater extent, while the backward reaction will occur at a lesser extent. Okay, forward reaction will occur at a greater extent, backward reaction lesser extent, so that we will have a net forward reaction. Net forward reaction. This is important. Okay. Net forward reaction. Okay? Now, notice the following. So, the equilibrium position here, we say that equilibrium position is shift to the right or to the product side. What do you mean by equilibrium position shift to the right? Now, this is how we describe the change that is happening on a system. Equilibrium position shift to the right. That means we have the forward reaction occurring at a greater extent than the backward reaction. Or that means there is a net forward reaction. Okay? This is just different ways of describing the change of a system. But I would like you to study and follow how I express, how I describe the changes and respond by the system. So equilibrium position is shift to the right. Okay? Favoring more of the product side. Okay? Now, the second one here, Kc, Kc, you remember Kc, Kc is the constant, basically looking at the product concentration divided by the reactant concentration. Kc remain unchanged since the temperature is the same. Now remember, Kc is temperature dependent, meaning that it will not change except temperature change. Okay, so equilibrium constant remain unchanged. This is very important. Sometimes the question may ask you, how does this changes affect the equilibrium constant? And the answer is no change, because the temperature remains constant. Okay. All right. Now, the third one you may also need to pay attention to. So you see, even the system has counteracted by lowering the reactant concentration. So even though the system has counteracted, the reactant concentration at the new equilibrium is still higher than original. Now let's have a look back to the graph here. Now you see, even though the system has tried its best to lower the reactant concentration, but when you look at the new equilibrium and you extrapolate backward, you see the reactant concentration is still higher than original. Okay? Now, very often I would describe this as what's done is done. Okay, I would say what's done is done. Okay? Because after all, you have added some extra R into the system. So even the system can respond by counteracting the increase in R concentration. Still, at the end, you should be expecting more R than before, because after all, you have added some R, right? So that's the idea. Very often, when students sketch this graph, they intended to have the new equilibrium where the reactant concentration is the same as before, because they think that, oh, the system will counteract so that everything goes back to original. Everything goes back to original. But this is not correct, because what's done is done. There is actually a change on the system. The system, according to the Chatelier Principle, the system is simply trying to minimize the change, but it cannot remove the change. So bear in mind of that. Okay. So also underline that one. The reactant concentration at the new equilibrium is still higher than the original. Okay. So that's the idea. Now, so you realize that for the Chatelier Principle, you need to first identify the change, and the system will change by counteracting. And how a system can actually respond? Actually, the system can only do two things. One, shifting the equilibrium to the right, to the product side, or shifting the equilibrium to the left, to the reactant side. This is the only two possible ways a system can respond to a change. Okay? Now, when there is a change going on, then we need to describe how does the system change. When we have to describe the changes on a system, two things we have to pay attention to. One, equilibrium position. Is it on the right? Is it shifted to the right? Is it shifted to the left? Or does it remain constant? Also, equilibrium constant. Does it change? Does it increase, decrease, or stay the same? So very often you need to consider these two items related to equilibrium system. Okay? Now, let's have a look at the next page. Alright, so you know the drill, pause the video, attempt the question, and then resume the video and check the answers. Alright, let's have a look. We have a reversible reaction like this and an equilibrium mixture. Now already in equilibrium, we have this concentration of this, so it is 1.2, 0.5 of this one, and 0.3 of CO2 plus. Okay? This is all at equilibrium. Now, the student add 0.5 mole of sodium chloride into the mixture and stir thoroughly until all the sodium chloride has dissolved. Okay? So this one must be the change. Right? Right. So explain how equilibrium position and equilibrium constant will change upon the addition of sodium chloride. Okay. Now you need to explain how these two items changed. First of all, we need to identify the change. So the change is need to mention, 1, the concentration of chloride increases, right? You need to clearly identify the change. Adding 0.5 mole of sodium chloride will increase, okay, will increase the concentration, okay? Now, down here, we also have to mention about the equilibrium position. So the second one, we say that the equilibrium position, okay, will shift to the right, okay? Now you also have to explain, okay? So net forward reaction consume Cl minus and lowers the Cl minus concentration, okay? And 3, you need to mention about the Kc. So Kc, will it change? Qc, okay, remains constant, okay? Because temperature doesn't change. It's unchanged. Okay? So this is how you explain the change on a system upon a change. Okay? Alright, so down here, we need to sketch how the concentration of each chemical species change upon the addition of sodium chloride. Indicate clearly on the graph the time when the new equilibrium is reached. Okay? Now, well, let's just say it is 1 dm cube. Let's just say it is 1 dm cube solution. Okay? So, at the beginning, you see the changes happens here, right? The changes happens here. So, we need to, first of all, draw the part of the original equilibrium system first. And we need to show the changes only when the curve reaches this point, isn't it? So I will use different color. Perhaps I will use, first of all, cobalt. Cobalt, I will use red, perhaps. So cobalt starts with 0.3, right? So 0.3 probably here. Okay, we can draw a reference line to help ourselves, because this is the part where the changes occur. Okay, so the red one is the cobalt, and then the chloride, I will use green. Okay, the chloride is 0.5, so it's over here. Okay, and then we also have our product, which is the complex ion, 1.2. Okay, let's do it here. Okay. Now, when we add the sodium chloride, of course, suddenly we have a lot of sodium chloride. So we will add, perhaps, it jumps all the way to here, okay, to 1, okay, because it's 1 dm cube. Okay, adding 0.5 mole will basically increase the concentration by 0.5 mole per dm cube. Okay, after that, there must be a change. There must be a change going on. So you can focus on the chloride first, because the chloride concentration must decreases. But bear in mind, it should not go back to the original level. So here, what I will do is, I will set up another reference line. And this one basically, when the new equilibrium is reached. Okay? So over here, the green one, well, it will decrease. Okay, I think it will decrease to this point. So I think I will simply draw it like this. Okay, and the rest here should be flattened. Okay. Now, when the chloride has been consumed, the cobalt will also be consumed. Let's just put down here, Cl minus. The cobalt will also be consumed because they are both the reactants, right? So this one will also decreases. Now, however, you need to pay attention to the equation, the stoichiometry, because now you see 1 to 4 to 1, isn't it? 1 to 4 to 1. So when this one decreases by by 4, then this one will only decrease by 1, okay? Because for every 4 chloride ion being consumed, it will only consume 1 cobalt 2 plus ion, okay? So you need to pay attention to the here, the magnitude of decrease, okay? So if this one is 4x, I just make up a number. If this one is 4x, then over here, when you have to illustrate the decrease, then over here, you should only showing you x, okay? You must be drawn on scale. Of course, they will not be that straight, but at least you have this idea in your mind. Okay? And lastly, the product, of course, will have its concentration increased by a small amount, and this one should be equivalent to X as well, because this one, cobalt 2 plus and the complex ion are in 1-to-1 ratio. Okay? So this one will increase rapidly at the first place, and then generally flatten off. Okay? Okay? So this is how it looks like. Right? Now pay attention to how you draw the graphs. The graphs must be following what we have learned from the topic rates of reaction. Reaction goes fast at the beginning and slowly flatten and level off towards the end, towards the new equilibrium. Okay? Alright. Next page. Alright, so like I said, this part is talking about factors affecting chemical equilibrium. So we need to know what factors are we focusing on. So concentration is one of them, and later on we will talk about temperature, and then later on we'll talk about catalysts. Okay, so 3 factors. So here we will start by looking at the concentration changes. Now concentration changes, there are 3 situations where the concentration can be changed. We can add or remove reactant or product. Okay? We can change the volume and pressure, and this one is exclusively for gaseous system. Okay? And lastly, the dilution, talking about some aqueous solution. Okay? Now the first one, add and remove, this one should be very obvious. Let's just say in this equilibrium system, when we add hydrogen gas, then the concentration of hydrogen increases, equilibrium will definitely shift to the right, because by shifting to the right, it will consume extra H2 and therefore lower the H2 concentration. Okay, so it will shift to the right, and therefore it will net for reaction consume H2 to lower H2 concentration. Okay. Now at this point, I would like to ask one question: if such a changes happen, what do we expect to observe? What do we expect to observe? When we're comparing the original equilibrium to the new equilibrium, what would be the difference in observation? Now here, these are all gas, right? These are all gas. And iodine vapor should be purple in color, right? So originally, the mixture should be purple. And when we add hydrogen gas, it will shift the equilibrium to the right-hand side, so the concentration of iodine decreases. Therefore, at the new equilibrium state, we should expect the mixture to be less purple, or the color intensity of purple color decreases. Okay? Now the second one, change in volume or change in pressure. And this one is exclusively for gaseous sample. Now here, we further break it down into 3 situations where the volume or pressure could be changed. Okay? But first of all, for gas, you can think about volume and pressure. I mean, pressure is basically the concentration of gas. Okay? There's a little bit difference, but you can take it this way. And you also notice that the number of mole of gaseous molecule is directly proportional to the pressure. Okay? Right? So make sure you know N is directly proportional to P. Okay? Now, down here, how can we increase the pressure? How can we increase the pressure? Okay? Well, we can increase the pressure by decrease the volume of the container. For example, you see this one versus this one. If we press down the piston, the number of mole of the gaseous substance does not change, but the volume decreases. So the pressure also increases. You know, not only N is directly proportional to P, but P is directly proportional to 1 over V. So it's reversely proportional to each other. Now, so this one is one way to increase the pressure. The second one, increase the volume of gaseous reactant or products. Well, simply you feed in more reactant or feed in more product. In that case, that would be very similar to what we have in here, adding or removing reactant or product. Okay. The third one is to add an inert gas, such as a noble gas. But I can tell you, this one has nothing to do with the equilibrium, simply because the noble gases is not part of the system. So if you increase the pressure by introducing an inert gas, it has nothing to do with the equilibrium position or the Kc. Okay. Now, let's just say we have this gaseous reversible reaction. So let's just say this mixture is kept in a cylinder with a movable piston as shown above, just like this. When the piston is pushed, the volume decreases and the pressure increases, right? Like I said. To counteract the increase in pressure, then the equilibrium position, how does it shift? Well, you may think, hey, if you increase the pressure, you want to lower the pressure, right? But like I said, a system can only change in two ways, either shifting the equilibrium to the right or shifting the equilibrium to the left. There is no another option where it can decrease the pressure directly. So how the system will change in response to an increase in pressure? Well, we need to make use of this. N is directly proportional to P. That means you have more gaseous molecule than you have a higher pressure. So in other words, if you want to lower the pressure, you want to lower the number of mole of gas, isn't it? So here, to counteract an increase in pressure, need to highlight this one. To counteract an increase in pressure, the equilibrium will shift to the side with fewer gaseous molecule. We shift to the side with fewer gaseous molecule. Now here, if you look at the equation, we have 1 mole of nitrogen reacting with 3 mole of hydrogen gas. So altogether there are 4 moles of gas. Okay? And on the right hand side, it forms 2 moles of ammonia. So only 2 mole of gas. So you think about it. If the equilibrium position is lying all the way to the right hand side, that means basically all of the molecules will be ammonia. Then you will have the fewest number of mole of gaseous molecule, and therefore you will have the lowest pressure, isn't it? So here you will shift the equilibrium position to the right hand side because the right hand side has the fewer number of mole of gaseous molecule. So here, since there are 4 gaseous reactant molecule and only 2 gaseous product molecule, so the equilibrium position will shift to the right. By doing so, the overall number of gaseous molecule decreases, therefore lowering the pressure. Okay? So this is how the equilibrium will adjust itself towards a change in pressure. Okay? Shift to the side with fewer molecules, therefore you lower the pressure. Okay? And next time if you decrease the pressure, because next time you can pull out the piston, right? You can pull out the piston. If that is the case, the equilibrium will shift what? Will shift to the left. Because by shifting to the left, you can end up having more number of mole of gaseous molecule, therefore you are increasing the pressure. Okay? And like I said, adding an inert gas does not affect the equilibrium position. Okay? Now, what about Kc? Does it affect Kc? Well, the answer is, of course, no, because the temperature doesn't change. Kc will only change when the temperature changes. Okay, bear in mind of that. Now the next one here, dilution. Dilution. So let's just say we have a reversible reaction like this. This is basically the ionization of ethanol acid in water. Now here, let's just say we add water to the system. Now you will say, sir, I know that when you add water, the equilibrium will shift to the right-hand side. Because water is a reactant. You add more water, that means you increase the reactant concentration. But, however, you think about it, water is not only the reactant, but it is also the solvent. So, when we consider the Kc, if you remember the Kc, we have only the two products concentration multiplied together divided by the concentration of ethanol acid. So, we can't say that the concentration of water increases, so the equilibrium shifts to the right. We can't do it this way. Now, here is the part where we say that when we add water, actually the change is that all the reactants will have its concentration decreases. Okay, all the reactant concentration decreases. So this one decreases, this one decreases, this one decreases. So how can we tell whether the equilibrium will shift to the left or right when every concentration decreases? Now, the idea is that if you look at the Kc expression, the product, these two would decrease more significantly than ethanol acid, isn't it? Right? So, therefore, you will basically have a net decrease in product concentration. So the equilibrium position will shift to the right, okay, to counteract the greater decrease in product concentration. Okay. Another way of saying is that when you add water, you are lowering the solute concentration. You are lowering the solute concentration. So you want to increase the solute concentration. You want to shift to the equilibrium to the side where you can produce more solute. In this case, we have 2 moles of solute on the right, but 1 mole of solute on the left. So that's why it will shift to the right-hand side. This is another way to deduce whether the equilibrium position shift to the left or shift to the right. Okay. And you see here, for ethanol acid, 0.1 mole per dm cube, the percentage ionization is 1.3, but for 10 times diluted ethanol acid, actually more percentage of it can be ionized. Okay? So remember, again, when there's a concentration change, you need to think about what is the change first, and then decide how the equilibrium position can shift, such that it can counteract the change. For concentration, that is simple. You just want to, if the concentration has increased, then you just decrease it. Okay? But here, if you come across pressure, then you have to think about the number of mole of gaseous molecule on reactant side and the product side. Okay? Remember, number of mole of gas is directly proportional to the pressure. Okay? Now, next page here, we have a practice question. So again, spend some time working on the practice question, and then we will quickly check the answers. Alright, let's have a look. Again, we have this reversible reaction, and these are the changes. How does it affect these values? So if we add AgNO3, now AgNO3, it has nothing to do with these species directly. But remember, Ag plus can precipitate with chloride. So if this one precipitate with chloride, you're taking away the chloride ion, Aq, right? So basically it results in a decrease in chloride ion concentration. Okay, so chloride decreases. So the equilibrium will shift to the left. Okay, and this one remain unchanged. Okay, no change because the temperature doesn't change. If you're smart, you realize that they are all doesn't change. It all doesn't change. Okay. Now here, if we add small amount of cobalt, the complex ion, then of course equilibrium will shift to the left. Okay. So here, ammonia is condensed and pumped away. You take away product, so it will shift to the right. Volume of the container increases. Now you think about it. V increases, that means P decreases. So if you want to counteract a decrease in pressure, you want to increase the pressure. by increasing the pressure, you shift the equilibrium position to the left because the left-hand side has more number of mole of gas. So here you shift to the left. Argon has nothing to do because argon is not part of the system. Now down here, this is a tricky question, I would say. Now here we have an equilibrium mixture of the following reaction contained in a syringe with a movable piston. The nozzle is sealed. Now here, I will draw this setup on the right-hand side. Okay, so basically we have a syringe with a movable piston. Okay, and this one is sealed off. Okay, and inside we have NO2 plus N2O4, and this one is brown in color. Okay. Right. So what is the color of the equilibrium mixture? Of course it is brown. Okay, of course it's brown because brown and colorless will make it brown, definitely. Now state and explain the observations when the piston is pressed down. Now you notice this question has 4 marks, right? Based on what we have discussed, usually we mention about 1 changes, right? And then the shift to the one side. It can't really give you 4 marks that much, isn't it? So there must be something tricky going on. Okay? Now here, actually the tricky part is because there are 2 observations and 2 corresponding explanations. Now, first of all, let me deal with the equilibrium part first. So here, when we press down the piston, what is the change? Well, when you press down the piston, so the volume decreases, therefore the pressure increases. So you may think, when the pressure increases, you want to bring down the pressure according to the Chatelier Principle. So you will shift the equilibrium to the side where there are fewer gaseous molecules. In that case, that would be the right-hand side, the product side. So you will shift the equilibrium to the right because there are fewer gaseous molecules on the product side than the reactant side. Therefore, the pressure decreases. Now, if you answer it this way, you will get 2 marks, but you can't get 4 marks in total. Okay, so let me show you. Now here, when you press it down, okay, you press it down. Now let me just draw some molecules, shall we? So I will use orange to represent, and the other one I simply use the black ball pen. Okay. So at this stage, you will expect to see some NO2, some N2O4, like this. Okay, so it should be brown. Okay, it should be brown. Okay. Now when you press it down like this, the molecules, did you notice? They are more close together. They are more close together. They are getting pushed towards each other. So at this moment, at this instant, actually the concentration of NO2 increases, right? Therefore, it should be dark brown, isn't it? It should be dark brown, okay? Simply because volume decreases, so the concentration of NO2 increases. Okay, so actually this is the instant change. This is the first observation. Okay, at the moment where the piston is pressed, it should be deeper in color, so it becomes dark brown. But if we provide enough time, because like I said, equilibrium takes time to reach. So after some time, then the equilibrium will adjust itself. So here, what you expect is 2 NO2 will react with each other to form, okay, 1 colorless N2O4. Okay, so this is what we expect to find, okay, after some time. So here you see having fewer brown NO2, the overall gaseous mixture should be pale brown. Okay, and the reason is because when the pressure increases, then according to LCP, okay, it wants to have pressure decreases, right? Counteract the change. So it will shift to right. Okay? So a net forward reaction. Okay, so NO2 decrease, N2O4 increases. Okay, so the total number of gaseous molecule will decrease. Therefore, the pressure decreases. Okay, and this one is exactly counteracting the change. Okay, so this is how it works. So here, for this particular experiment, is quite tricky because there are two changes occurring. The moment where the changes have added to the system, and after the new equilibrium has attained it, there are two observations. So you need to pay attention to tricky situations like this. Okay. So here, I'm not going to write it down. You can simply translate what I have shown you here into a sentence using your own language. Okay. And part C here, briefly explain why the nozzle of the syringe must be sealed, because we want to make sure a closed system for equilibrium to attain. Okay. One precaution, so you will carry out experiment in fume hood as NO2 is toxic. Okay, or you can ensure well ventilation or good ventilation. Okay. Right. So that's it for the video.